I will talk a little bit about the pitfall of FFT, fast Fourier transform, and spectral density in the Python. It's summarized from the year of me doing a synthetic diagnostic, and there's a lot of mistake make. I think it will be useful for y'all to not make the same mistake that cost me months of my research. So pitfall 1, make sure that your data type is correct once you have once you preset a data array. And for uneven time spacing, you need to interpolate and then do the Fourier transform. Otherwise, it will not give you the desired result. And the FFT output frequency is not monotonically increasing, and also a is not equals to a square root of a square, because of if a are a complex number. And also interpolation for FFT has need an extra factor to make it correct for the purpose, actually for everything, and also for the purpose of summing over the frequency. First pitfall, if you choose the preset, the array, you have to set it to data type equals complex. Otherwise it will assume it to be the array to be float. Say the left is original, the left plot is original function. The middle is I preset it without specified data type. It will assume to be a float, which only have a real part. And this is the correct way. On the right, take it as define it as a complex number. And pitfall 2, uneven time spacing. If our time space on the right plot, the spacing of time is like the blue curve, then if you do the Fourier transform, it will look like this, which in reality the correct after the interpolation, it will be like this, will be two frequency spike. Will be two frequency spike, and then if you assume and just put in the frequency, put in the function of frequency of time, and the time is not evenly distributed, and you didn't interpolate it, you will get incorrect FFT result. So make sure that it's evenly distributed, and also sort it to monotonically increasing. And if you sort it, make sure that you sort it so that the time is still a float, and the function is complex. You can do the set data type. You can check on Python script, and you can also check on my pitfall scripts in my GitHub repository. I will put a link in the description. And pitfall number 3, FFT output frequency is not monotonically increasing. The original output of FFT in NumPy is a blue curve, like that. It will give a huge trouble when you are trying to produce once you try to interpolate the function. You can see that the blue is to interpolate that the functions of the frequency is not monotonically increasing. It's across the board 0. And if you sort it, the frequency from 0 to from however time to however time, then however frequency monotonically increasing, then you will have the correct data to be interpolated from. So it's important to sort it before the set. And also I have and coupling with this this video, I will have a manual on on the FFT tool that I created. And the pitfall number 4 is very sneaky. That's why you need to pay extra attention to. Is a not equal to square root of a square. Because the conventionally the angle in the complex plane is defined from negative pi to pi. So if you square it and it go out of the bound, it will be recalculated to falling into the range that is by default, that is conventional. And then you do the square root, then the answer is not necessarily correct. Here's an example. A equals 2 e to the 2 plus I 2/3 pi, and it's equals to this, obviously. And if you square it, it will be 4 pi 4/3 pi, but 4/3 pi is not within the range of negative pi to pi. Then we have to minus 2 pi. Then we ended up getting negative I 2/3 pi. And this is what will happen. And then we do the square root. We'll have 2 e to the 2 minus I 1/3 pi instead of e to the 2 plus I 2/3 pi. See, from this simple example, we see that a is not equal to a square root of a square. Why does it matter for our purpose in computation and synthetic diagnostic? Is that if you do something, if you sum some quantities, complex quantities with square, like sum everything with square and then do the square root, then it will not look like a smooth function. They can jump. Sometimes it can jump from negative to positive, from positive to negative. It's not a continuous. Plot. Sometimes it can. For me, I find that it gives me almost double the frequency from this effect, and it's very dangerous. Because it's there's nothing wrong with your code, and it's really hard to find. So keep in mind, a is not equal to a square root of a square. And just like this, here is the script on the upper left corner. There's a script, and that's the original function, and it did the square root of the square, and it looks like this. And if you do the FFT of this function, it will give you pretty much junk. I mean, it has something useful, but in a degree it's useful, but it has a lot of junks to it, so it's pretty much not useful. So make sure that you construct your script such that to overcome this or find a way around it. And the pitfall 5, interpolation. If you interpolate a FFT, if you sum over the frequency range, you will find that if you interpolate, say, like the frequency df, the frequency step df halved after the interpolation, you should multiply of a factor 0.5 of the height of the function, because the Fourier transform you do is to sum over each dot, right? Then you need to if you have more data, you have twice as much data points, then you should have half of the height. That's why you need to multiply a factor of a float of original frequency, length of frequency array, over the float length of a interpolated frequency array length. And that will give you the correct answer, somewhat correct answer, which up to the certain degree. and that's all. So those pitfall are very useful. So maybe before you commit to your GitHub or try to create a synthetic diagnostic, make sure to check all the 5 pitfalls that you might potentially stumble into. And next video, I will talk about some standard ways to benchmark with your synthetic diagnostic scripts.